Ladies and gentlemen, welcome to today's webinar. The title of this webinar is Radar Signal Generation up to 2 GHz bandwidth for single-channel and multi-channel receiver testing. Let's look at the table of contents about what we'll talk in this webinar. First of all, I will talk about radar signals. I will talk about wideband radar signals with 2 GHz bandwidths, and I will talk about phase transitions from pulse to pulse. The second topic will be real-time sequencing in order to achieve ultra-long play times. Then I will talk about scenario generation with the RNS pulse sequencer software. We will see examples of multi-emitters and background emitters. We will see direction finding scenario simulation for testing of multi-channel radar receivers. And I will talk about timing accuracy and repeatability of the measurements. And last but not least, I will conclude my talk and give some information for further reading. So first of all, let's look at real-world scenarios and what needs to be simulated. First of all, of course, we need to simulate the signal waveform. It consists of pulses, sequences of pulses, bursts, maybe modulation on pulse. Inter-pulse modulation in order to achieve frequency agility or PI agility is also needed sometimes. Then, of course, in real world, there are transmitters and receivers, and they have an antenna pattern. And sometimes they also have rotating antennas. So antenna patterns have to be considered. If antennas are rotating, antenna scans have to be considered, like spiral scan or helical scan. Of course, each antenna has its polarization, so also polarization has to be considered in the simulation. Then, of course, receivers can be single-channel or multi-channel. Every transmitter and receiver has a location, has an attitude information, and has a certain antenna pointing. And, of course, as the transmitter and receiver are not at the same location, an appropriate propagation model has to be in place in order to account for free space loss between the transmitter and the receiver. So first of all, let's look at the radar signals. First, I would like to look at the FMCW radar and derive its key requirements on the signal generation side. FMCW radars sweep the frequency over a certain bandwidth. If there is an object, there will be a radar return. If the object is moving, there will be a Doppler offset on top. The principle can be seen in the following figure. The beat frequency, which is the difference of the current actual TX frequency and the received frequency of the echo, can be used in order to derive the range and the velocity of the object. More complex waveforms are needed for more than one object. Highly linear wideband chirps are required for good radar performance. So for all these requirements, a wideband digital baseband is the perfect solution in order to generate the wideband FMCW signals. In order to get more information, you can also refer to a Rohde Schwarz application note, which is highlighted in the top of this slide. There are not only FMCW radars, there are also pulsed radars. There are pulsed CW radars and radars with pulse compression techniques. So first of all, let's look at the pulsed CW radar. The resolution of a pulsed CW radar is directly depending on the pulse duration. So the longer the pulse duration is, the worse the resolution is. Or the shorter the pulse is, the better the resolution is. Short pulses give good resolution and are mostly used in short range distance. But there are also pulse compression radars. Pulse compression radars use modulation on pulse. So now the resolution depends directly on the used bandwidth of the pulse. So now also with longer pulses a good resolution can be achieved. And now good resolution is also available for longer ranges. So before directly looking at the signals, I will explain to you the setup which is used for signal generation and signal analysis for the wideband signals. The signal generation is done with the RNS pulse sequencer software, which is used to define the radar signals. The signal generation is done with SMW200A and its new internal wideband baseband hardware with up to 2 GHz bandwidth. Once the signal generation is done, the signal is transferred to the FSW with its option B2000 to do the signal analysis, together with the RTO. So first of all, we have an example of an FMCW signal with 2 GHz bandwidth. On the left-hand side, you can see the spectrogram. On the y-axis there is the time domain, on the x-axis is the frequency domain. So you can see a couple of FMCW sweeps over 2 GHz bandwidth. On the right-hand side, the FMCW signal is given in time domain and together with a linearity measurement. Again, on the y-axis here, you can see that 2 GHz bandwidth is used for this FMCW sweep. At the bottom of this figure, a linearity measurement is shown. Linearity means how big is the deviation from an ideal linear chirp. So here it is very low, so this means that this is a very good and highly accurate signal. Before, we also talked about pulsed radars. So here's an example of a pulsed radar with modulation on pulse. Here I used a chirp signal with a chirp rate of 1 MHz per nanosecond. The pulse length is 2 microseconds. On the left-hand side, the top, you can see the individual pulses which have been captured. At the bottom of the left-hand side, you can clearly see the 1 GHz frequency sweep during the pulse. On the right-hand side, there is the associated quadratic phase for this pulse. And on top, you can also see that there are many evaluations available with FSW to look into more details of the pulses. Up to now, we have only talked about single pulses at a single frequency. But radar systems change instantaneous frequency to avoid detection, jamming or interference. So therefore highly HL frequency switching is required. Also for this, the wideband digital baseband is a perfect solution. Here's an example how this can look like. In this picture here, you see 11 frequency hops from left to right. So each frequency for each pulse is different. The bandwidth of the hopping signal is 2 GHz, and the total duration for this hopping scenario is 22 microseconds. In this example, each chirp had 25 MHz chirp bandwidth and 2 microseconds pulse duration, and the PRI was also 2 microseconds. So this in total results to a hop rate of 500,000 hops per second. In addition, as this baseband hardware is so flexible, we can also combine pulsed signals and FMCW signals. This is extremely important, for example, in order to test radar warning receivers, which must be able to cope with pulse signals, FMCW signals all together. So therefore, digital baseband hardware is also a perfect solution. In addition, overlapping signals can be simulated. And here another example for this. On the left-hand side, we see a hopping radar, which is doing a frequency hop from pulse to pulse. In the middle, there's an FMCW radar, and on the right-hand side, there's another FMCW radar. So all these signals can be produced with a wideband baseband hardware and a single RF chain in the SMW200A. Up to now, we have only looked at the standard modulation types like FMCW or chirps, but there are also other modulation types. On the left-hand side, you can see a Barker code R13. Barker code means the phase is switched by 180 degrees over with a certain series, like you can see here in the picture on the left-hand side. Also, Barker codes can be used for pulse compression in order to achieve good resolution. In addition, you can also have piecewise linear chirps with different chirp rates during the pulse. Also, this helps radar engineers to design more accurate and more reliable systems. Up to now, I have only talked about single pulses with large and wide bandwidth. Now I will talk what's happening from pulse to pulse. So here we will have a detailed look at phase transitions from pulse to pulse. So why is this necessary? Why is this needed? First of all, modern radars use frequency agility for changing the center frequency in order to avoid detection or jamming. Radars normally use one common reference synthesizer in order to preserve the phase. And also for radar processing, it is necessary to have a defined phase for each pulse. So therefore, in order to achieve this, the wideband baseband is perfect because you have total control of amplitude and phase for all of the signals which you are creating. In addition, there are fast-hopping synthesizers which can simulate frequency agility and can preserve the phase value for each pulse. Fast-hopping synthesizers can simulate multiple emitters by switching among them, which might lead to dropouts if you have too many emitters. Wideband digital baseband is a perfect alternative for this application. So the phase value again can be calculated for each pulse in the digital domain, and multiple radar signals can be simulated in parallel with no signal dropout. Now let's look at an example of what's happening with phase if you have a hopping radar signal. Now let's assume there's a pulsed radar which has a certain carrier frequency in orange. Some pulses have an offset of this carrier frequency by delta F1. Some other pulses have an offset of this carrier frequency by delta F2. So frequency hopping is simulated by varying the offset frequencies in the digital baseband. Now on the right-hand side you can see how this looks like in the digital baseband. As the blue pulses have a certain frequency offset in the baseband and the red ones have another frequency offset, there is a certain phase curve visible. The start phase of pulse 3 and 5 shall be the same as if the signal had never hopped away in order to preserve the phase. The same is true for the blue pulses. With the memory effect, which is implemented in the software, this can be achieved. If we look at the third pulse, and if we look in the yellow circles, we can see that the phase of these pulses is exactly the same phase as if the signal had never hopped away. So this is how it looks like in the digital baseband domain, how we generate the signal. Now let's look at the same example and how it looks like in the RF domain. On the left-hand side of the slide, you can see a screenshot. There are two traces. The white trace is a trace of a signal which is not doing any frequency hopping. The yellow trace is a trace where pulse 2 has a different RF frequency for pulse 2 than for pulse 1 and pulse 3. Now with the memory effect implemented in the software, we can preserve the phase for pulse 3 as if pulse 2 had never hopped away. So you see, for pulse 3, the signal is totally overlapping, so the phase value is preserved for signal from pulse 3. In addition, we can also make it more complicated. So in addition to the hopping signal in the middle of our pulse 2, we can also apply a time shift. Also then, the phase value for pulse 3 is preserved. You can see that from the picture on the right-hand side that the phase for pulse 3 is overlapping, the yellow curve is directly following the white ones. So the phase value is preserved and the phase coherency can be guaranteed. Yet there is not only the memory effect which sometimes needs to be considered. There are also other phase transitions which might be needed. There are absolute phase transitions and there are also phase transitions which keep the phase of the sample, the last valid sample. On the top of this picture you can see how it looks like for absolute phase. So every pulse is starting with a defined phase, in this example 0 degrees. The other mode which we provide is the continuous mode. So the phase of the following pulse starts exactly with the same phase value of the last valid sample. So if you look in the picture you can see that after the pulse break the phase is continuing at the same value as it stopped for the pulse before. So up to now we have only looked at single pulses or a couple of pulses. Now the question is, how does the situation change if long scenarios have to be simulated and what has to be considered for long playing scenarios? So therefore I will present the real-time sequencing in order to achieve ultra-long play time. So now let's look at realistic radar signals which are used in the community. Realistic radar signals can have low PRIs or high PRIs, so both are used. They can have slow antenna turns in order to point your antenna for a longer time towards a target. Radars, as we have seen before, can use frequency agility in order to avoid jamming or detection. And of course, many individual pulses can be used. In order to produce such a signal, of course, the waveform capabilities of the ARP need to be considered. So, the play time mostly depends on the used bandwidth or the sample rate. For 160 MHz bandwidth, this is 200 megasample for the Rohde Schwarz signal generators. For 2 GHz bandwidth, it's 2.4 gigasamples. And of course, the resolution of the IQ data needs to be considered. On the right-hand side of this slide, we can directly see how the bandwidth used and the sample rate used turns into available play time. From left to right, the bandwidth increases. The different colors show different memory depths of your ARP, for example. So, with low bandwidth signals, you can play for a long time, but the wider your signal gets, the less playtime you can achieve with your ARP. This means, for example, for HL signals, you cannot play them too long because your ARP memory is not sufficient. So therefore, in order to overcome this problem, sequencing is a good solution. Sequencing can achieve ultra-long play times by manipulation of basic pulse waveforms via control lists, which we also call sequencing lists. These lists include amplitude changes, phase changes, off times and offset frequencies. This is very useful to produce signals with slow antenna turns, long PRIs, all large frequency offsets because you can save ARP memory size with this principle. CW signals, Barker codes, and chirp signals can be calculated in real time with this sequencing tool from Rohde and Schwarz. In the next example, I will show you how this looks like. First of all, let's assume an emitter which is having a circular antenna scan with 5 seconds scan duration, which is quite long. The carrier frequency of this radar is working at 3.04 GHz. It has burst-to-burst RF agility. The hop width of each burst is 10 MHz. It's also using PRI agility, and the pulse duration is also not always the same, but varying during the scenario. In addition, each chirp is using a linear frequency modulation with 2.5 MHz bandwidth. So, summing up all these points and items, this would translate into a very large waveform if we assume that we have to use 200 megasamples from the ARP and that the signal duration is 5 seconds long. So this more or less translates into a total waveform size of 1 gigasamples, which is quite a lot. So with extended real-time sequencing, you have a perfect solution in order to minimize calculation time and, of course, ARP file size. At the bottom of this slide, a preview is seen how this looks like. Here you can see the envelope of the expected signal. Here I'm using a sinus X over X antenna, which is doing a circular antenna rotation. So from peak to peak, you can see the 5 seconds. I've recorded some more seconds in order to see how the total signal looks like. So whenever there are no side lobes of the antenna, there's also no signal. I've assumed an antenna which does not have any back lobes. And here is how we do this. So instead of calculating a long waveform, we do it differently. We only calculate a control list which has the pulse width duration, which has a certain attenuation, which has a certain frequency offset and a phase offset inside. In addition, it carries what kind of modulation it is, and it also carries a time of arrival information. This means with this control list, we reduce the required waveform size totally to a very little value and can do the signal generation in real time in the ARP of the signal generator. This brings down the waveform size dramatically. In the following example, I will show you a direct comparison between ARP-based signal generation and signal generation using the extended sequencing features of the SMW200A. So first of all, let's look at the scenario. The scenario consists of an emitter, which you can see here. The emitter is using a sinus X over X antenna, and it has a circular scan, which is 5 seconds long. Here you can see that this translates to 12 rounds per minute. In addition, we can also have a look at the signal. The signal has been described before. It's using quite a lot of agility, which can be seen here. So there are frequency steps, there's PRI agility, and also the pulse width is changing. This has all been defined in the signal here. At the bottom of this slide, you can see an overview how the signal looks like. Now we have to choose the kind of signal generation which shall be used. So first of all, we have to access the signal generation dialog. And here I will use extended sequencing, which will bring down the memory size dramatically. So this has already been pre-selected, and now I only have to hit the calculate and upload button and the signal generation starts. You see how quickly it works. Once this has been achieved, you have to press the run button and the signal is transferred and started in the ARP of the signal generator. So this was really very quick. In the next slide, we will see how it looks like for ARP-based signal generation. We are using the same scenario, but instead of using the extended sequencing mode, I'm now using the ARP mode. So I will go back to a simple creation of an ARP waveform. And of course I have to select a certain sample rate, though in this case I select 200 MHz in order to create a decent signal quality. Also here, I have then to select and start the calculate and upload button after the definition of the signal. In the next slide, I will show you a direct comparison of the performance using the extended sequencing capabilities of the SMW200A and a pure ARP-based signal generation. So, both scenarios are the same. The calculate and upload button has been hit at the same time. On the left-hand side, you see that the signal is calculated very, very quickly. It's already uploading to the signal generator, whereas on the right-hand side, the ARP-based signal generation is still taking its time, creating a large signal. If you can read the values, you will see that it is roughly 1 gigasample memory size, which translates into 4 GB of data. So now it's also uploading, and in total, the duration of the extended sequencing was only 11 seconds from hitting the button for signal generation and running the signal on the SMW, whereas it takes several minutes for the pure ARP-based signal generation, which is quite unhandy. In the third section of this webinar, I will show you how to do scenario generation with the RNS pulse sequencer software. There we will have a couple of subtitles. First of all, we will look at multi-emitter and background emitters. Then we'll look at direction finding scenario simulation for testing of multi-channel radar receivers. And then at the end, we will look at timing accuracy and repeatability of the setup. So first of all, let's look at a typical multi-emitter scenario. In a multi-emitter scenario, you have an aircraft flying somewhere. You have ground-based radar, which is detecting the aircraft. On the other side, you have also other radar signals occurring. So many of these radar signals might be threatening radar signals or might also be friendly radar signals, so you don't know as a pilot. So you have to ask yourself the question, is it a friend or is it a foe? Do I have to abort my mission or do I have to get out of this situation here? So therefore, these aircrafts use radar warning receivers which help to identify the radar signals and classify the radar. The radar warning receivers are needed to be tested thoroughly in order to make sure that they also work in all circumstances. And therefore, meaningful radar signals are needed in order to test the radar receivers thoroughly. So now let's look at realistic radar signals. Assume the scenario consists of FMCW signals and pulsed radar signals. In this example, I'm using 4 FMCW signals simultaneously. They are offset in center frequency, have different sweep rates and sweep durations. Then there are 3 pulse signals with low, high and medium PRI, which are offset in time. So they have agile PRI. And here's how we can generate the signal. Generate all the FMCW signals in baseband A and generate all the pulse signals in baseband B. The FMCW signals are shown in the red box, the pulse signals are shown in the blue box. Then combine all the signals digitally inside the SMW200A and output them at RF port A. In order to generate the signals, the pulse sequencer software was used to create them. This is a good test case to simulate pulse collision of several radar signals without pulse dropping in a very heavy populated spectrum. I use a wideband receiver and some analysis software to look into the generated signals in detail. In the lab, you could inject them into your DUT. And here is the measured result. In the top, you see the measured spectrum, and the bottom, you see the measured spectrogram. In the red circles, you see the 4 FMCW signals with different bandwidths and with some offset frequency in between of them. In the bright blue circles, you can see the pulse signals with a characteristic sinus X over X spectrum. They are not active at the same time, but they have a certain time offset delta t, as can be seen in the spectrogram in the bottom of the figure. In the spectrogram, it can be nicely seen that the FMCW signals are always on and populate the band, whereas the pulse signals occur according to the PRI used. With a digital receiver in place, one has the possibility to look into the received signals and identify them. If we look into the FMCW signal, there is a typical FMCW sweep visible. Here, only a simple sawtooth format is used with 20 MHz bandwidth. FMCW signals are constantly on, and the receivers tend to lock on the strongest signal, so they desensitize for pulsed signals, which have a lower power levels in average. More interesting is what the airborne radars are doing. Let's have a look. This figure shows the pulse number on the x-axis. This means every single pulse is a count. On the y-axis, you can see the pulse repetition time, or PRI, as we also call them. This radar uses low PRI mode, which is good for long-range surveillance, which you can see on the right-hand side. One red bar corresponds to the amount of pulses that use the same PRI. This is called dwell. Each dwell consists of 1000 pulses. This radar switches the dwell 3 times. It means that this radar mode uses 3 different PRIs from 100 microseconds to 110 microseconds up to 120 microseconds. Therefore, you can see the 3 white arrows which indicate the switchover. Let's look into the next pulsed radar signal. The figure is the same, just the scale is different. Now this radar uses high PRI, which is a typical air-to-air mode for high Doppler frequencies. With high PRI, the unambiguous range is very high, which is mandatory for that radar mode. There are 5 dwell switches, so the PRI is changed 5 times. Again, one dwell has 1000 pulses. If you remember, there was a third pulsed radar, so again, let's look also at the third one. This one can be seen here. Now the scale on the y-axis is also different again. This radar uses medium PRI, which is good for look-down operation of airborne systems. They have good clutter suppression in this mode. So in this case, again, 5 dwell switches are used, but now we only have 250 pulses per dwell. Let's discuss another radar scenario with total different radars. Here they are. One is a maritime moving target detection radar at 3 GHz using burst-to-burst RF agility. It uses agile PRI modes, agile RF, and it is using a circular scan on top. Details are shown in the red box. The other radar is again in X-band. It's a maritime patrol aircraft radar, which is used to detect small targets in rough sea, for example. It uses pulse-to-pulse RF agility and is using a bidirectional sector scan. And here is the setup how to generate the signals. Each radar signal is generated in one baseband. The maritime moving target detection radar is generated in baseband A within the red circle. The maritime patrol aircraft radar is generated in the blue circle, which can be seen in the picture below. Now they are added in RF as they are working at 3 and at 10 GHz with an RF combiner and injected into the wideband receiver. The wideband receiver is used to analyze the generated signals. Here are the details of the maritime radar and its signal. In the spectrum, you can clearly see 8 different RF signals. They are not on at the same time, but they are agile, so they are hopping. The power level is varying over time as there is an antenna scan involved. That's why you can see a max hold in the figure below and the green line, which is giving you the current or actual power level. Let's have a closer look. Again, I'm using the same analysis figure format as before, but it has different y-axis scales now. Let's discuss it. In green color, you can see 8 green lines. They correspond to the 8 agile RF frequencies, which change from burst to burst. Each burst now has 20 pulses in this example. In red, the current PRI per radio frequency is shown. Each RF has a different PRI. Look at the dotted lines. For the second and for the third RF, the pulse repetition time or pulse repetition interval is different than from the first RF. This you can see as it has changed its position. Look into the white circles. This longer PRI can be used to detect objects in longer ranges. This longer PRI is the time the radar needs to switch from one RF to another RF. In blue, the duration of the pulse is displayed. This radar is using 3 different pulse durations during its operation. And last but not least, the radar uses a rotating antenna. So in yellow, the received power levels per pulse are shown. So what you see here is the main beam of one circular antenna scan. We saw frequency plots, PRT or PRI plots, and pulse duration plots or amplitudes in one single window. This is possible as the y-axis can be changed so that all measurements can be shown in the same window, which gives you a good overview of the radar mode which is used. The fourth radar was in X-band and uses pulse-to-pulse RF agility. Here is the spectrum and the spectrogram. It consists of 10 individual RFs. Each pulse uses modulation on pulse with linear frequency modulation. This can be seen in the red circles. This radar uses a sector scan, which is bidirectional. To have a better understanding of the scenario, let's have a look at the 3D preview which is available in the pulse sequencer software. The object in the red circle is off the radar bore side, which is shown in blue. So it is not in the main beam. Over time, the beam hits the object twice, one time on the way towards the target, one time on the way back. So you can clearly see two peaks with a long break in the middle and the bottom of this slide. This is a simulation of the expected amplitude variation over time. And now let's also look into the measurement. And here is the measurement of what the receiver sees. In the middle, there are two scans, which are indicated with scan 1 and scan 2 on the white arrows. The object was hit 2 times, as you could see in the simulation before. Here, the amplitude corresponds into the yellow color, which is the amplitude of the received pulses. The RF is agile from pulse to pulse, which can be seen in the green color. So there's a change of frequency from pulse to pulse. The pulse duration is constant, so that's why you only see one single blue bar at the top of the picture. Up to now, we have only talked about deterministic radar signals, like FMCW signals or pulse signals. But in order to make your simulation more realistic, there might be background emitters needed, which act like a noise-like signal. What does this mean? Background emitter signals are signals which are coming from the background from our kind of radars. We propose a feature in this software which allows to define the statistics of background emitters. In this example here, you can see that I've defined 255 emitter signals within a bandwidth of 1.9 GHz. And I've also defined a certain duration. For the statistics, you can give the ratios of the pulse repetition frequency to the pulse duration, and you can also give a level range for where you want the radar signals to occur. Once you have finished the definition, you can also place your background emitter signals on the map where you normally have your radar emitters. If you want the background emitters to come from every direction, you can place them in the box on the left. If you want the background emitters to come out of a certain direction, you can directly place them on the map so that they look like that from one certain direction many background emitter signals are coming. The receiver is now receiving its wanted emitter signal in addition to the background emitter signals which act like a noise and which are also used in order to stress the receiver to get meaningful tests. Here are some screenshots how these background emitter signals can look like. I've used a 2 GHz wide baseband for this. So the total RF frequency I'm covering is from 9 GHz to 11 GHz. The snapshots are 200 microseconds long. If you remember the statistics which I defined before, you see that I've defined many emitters. And this can be seen in the different snapshots which occur at different points of time. So in this spectrogram, you see many emitter signals. Also in the frequency domain representation, you see many spikes. So all of these spikes correspond to a radar signal which are used as a background signal in order to stress the receiver. Up to now, we have talked about multi-emitters and background emitters, but we have only talked about single-channel receivers. Now, we will extend the receivers by more than one channel so that we end up in a scenario where you have to test multi-channel receivers. Also for this test case, the Rohde Schwarz pulse sequencer software provides the right features. So now let's assume again there's an aircraft flying and there's a radar transmitter somewhere in the space. So also this aircraft is carrying a radar warning receiver. But this aircraft also wants to know where the radar signal is coming from. So therefore it is using several antennas which look in different directions of the aircraft. So if we now look at the individual antennas, how much power, RF power level they are receiving, the purple antenna definitely will receive most of the power. The blue antenna is receiving less power, the green antenna even less, and the orange antenna is receiving a little more power. So this means that the radar receiver with its 4 channel is receiving 4 RF signals which have different power level. From these power levels, the radar warning receiver can now calculate the direction from where this radar transmitter is coming from and maybe warn the pilot not to fly there. In addition, if we do not only evaluate amplitude, we can also evaluate phase and time delay among the individual antennas. So let's use the same example as before. We have the sector antennas, the 4 sector antennas which are looking into individual sectors. But now, if the radar warning receiver is working in phase coherence mode, it can also evaluate the phase difference between the individual antennas. If the timing is accurate enough, it can also determine the time of arrival of each radar signal. In addition, use amplitude, phase and timing in order to find out where a radar signal is coming from. So this is giving much more information to the radar warning receiver than only looking at the pure amplitude. For these scenarios, the Rohde Schwarz pulse sequencer software has the right tools on board to simulate exactly test cases to test the radar warning receivers. Here's an example Here I'm defining the antenna configuration for a 4-antenna receiver. You can see on the left-hand side that there are individual DF antennas defined. Each antenna can have a defined location and a defined pattern and a defined gain value. In addition, the pointing of each individual antenna can be selected. Once you have defined all the individual antennas, you can preview them on a map. On the right-hand side, you see 4 individual antennas, and you see the pointing of the antennas, which is this small little arrow. At the bottom of the slide, you can see previews of the sector antennas which have been used for this application. So the antennas are all looking in different application in order to cover the 360-degree sphere of the aircraft around. So up to now, we have only looked at antenna patterns and antenna scans. But antenna polarization is also an important point to notice. Antenna polarization can have important effect on the received power level of the receiver. If the antenna polarization is not matching the polarization of the receiving antenna, there might be a considerable power loss in the simulation. So therefore, the pulse sequencer software also supports the use of antenna polarization for both the transmitter antennas and also the receiver antennas. How this looks like, I will show you in the following slide. The first part of the slide shows a perfect alignment of the receiving and transmitting antenna. So both polarization vectors are vertical. You do not see any power drop because both antennas are perfectly aligned. Now let's assume one of the antenna has a roll angle of 45 degrees, which leads to an antenna mispointing. So in this case, the change of the attitude through the aircraft flight maneuver, maybe, will lead to a power drop in the receiver, in this case of around 3 dB. If you even increase the roll angle to 90 degrees, you get a total misalignment of the antenna polarizations. So in this case, you are only receiving cross-polarization from the transmitter antenna. In this case, I've selected 30 dB of cross-polarization suppression. This value can be freely selected by the user in order to simulate its antennas used in the real system. Now, after defining all the individual items for the simulation, it's time to configure the signal generators. Although here the pulse sequencer software supports the user. On the left-hand side, you can see the 4 individual signals which have to be created for a 4-channel DF receiver. There's antenna 1 to 4, which can clearly be seen. Antenna 1 and 2 is connected to RFA and RFB. Antenna 3 and 4 is connected to additional boxes on IQ out 1 and IQ out 2. The connection diagram shows you how your signal generator setup looks like. The master is the SMW200A, which provides the 2 RF sources. SGS plus SGU can provide additional RF sources for multi-channel setups. They are fed with the IQ signals which are generated inside the SMW200A. So now you have 4 RF channels, and these channels can be then directly connected to the radar warning receiver, which in this case is having 4 channels. Rohde Schwarz is providing a reference solution for testing of multi-channel receivers. In this example, the setup consists of an 8-channel setup made up of 2 times SMW200A and additional SGS and SGU 100A. The SMW can be seen in the middle with the screen. In order to provide the additional RF channels, SGS and SGU are used. All the RF channels can be seen in the middle. There are 8 individual RF outputs up to 20 GHz. NRP Z81 power sensors are quite useful in order to check if the signal is there or if a cable is not working correctly. The signal definition is done with the R&S pulse sequencer software, which is running on this laptop. Now, after all the signals have been defined and all the setup has been cabled, it's important to know how good the setup is working. So therefore, I will look at the timing accuracy and repeatability of the signals. So this means how nicely are your signals time aligned whenever you trigger them, whenever you change them. So therefore, we will have some examples in the following slides. So here is the setup which I'm using. Again, I'm using a 4-channel setup. 2 channels are coming out of SMW200A. 2 additional channels, channels 3 and 4, are produced by SGS SGU. In order to find out how much jitter there is among the different channels, I'm using a ZVA. The ZVA is measuring channel 2, 3 and 4 in reference to channel 1. With this setup, I can find out the relative time delays between the RF channels, which need to be stable and reproducible. Absolute time delays between the RF channels can be calibrated via the IQ delay in the SMW200A and only need to be measured. For further reading, you can also refer to the application note, which is shown here on this slide. So now let's look at the results. Let's look at the relative time delay stability between the 4 basebands. For this, we have triggered the ARP 500 times and we have measured the stability among the channels. I've selected a low RF frequency in order to exclude any errors coming from high RF frequencies or the test setup itself. Here are 3 results shown. This is the jitter from channel 2 versus channel 1, channel 3 versus channel 1, and channel 4 versus channel 1. You can see that the standard deviation is only 1.7 picoseconds in the first, 2.5 picoseconds for the third channel in reference to channel 1, and 3.8 picoseconds for channel 4 in reference to channel 1. So, by using the baseband splitting of SMW200A, you get a perfect solution for 4 ultra-synchronous baseband signals. On the slide before, I have done the measurement at 1 GHz. But normally you're also using higher RF frequencies. So we have repeated the same measurement also for 10 GHz, for example. In this case, we have first looked at the stability of the ZVA itself, so without doing any retriggers. The results can be seen on this slide. So in this case, we have not retriggered the ARP. So the ARP is running all the time, and we have only measured the time stability among the different channels. So here we see a little higher standard deviations, about 13 picoseconds for the first one, 22 picoseconds for channel 3 to channel 1, and 20 picoseconds for channel 4 to channel 1. Now we have done the same before. We have triggered the ARP in addition, and you can see that there is almost no change from figure 1 to 2 and to figure 3. So this means that the measurement uncertainty of the ZVA itself is already larger than the error introduced by the individual split basebands of the SMW200A. So therefore, this error is not contributing anything to the total error budget. So with baseband splitting and the SMW200A, you have a perfect solution also for 4 ultra-stable RF channels up to 20 GHz. So in the last section of this webinar, I will give you a summary about the webinar and what we've talked about, and some information for further reading. In this webinar, I have introduced to you the new hardware capabilities of the SMW200A with its new wideband digital baseband. In addition to the wideband baseband, you can have also 2 times 20 GHz RF channels in one box, which we have seen for the direction finding tests. Single channels can go up to 40 GHz. We can also produce phase coherent signals up to 40 GHz with the SMW200A. The R&S pulse sequencer software gives you all tools which you need to generate radar signals. They can be wideband, they can be narrowband. Real-time sequencing is giving you a big benefit in order to achieve long play times for your scenarios. The pulse sequencer software also supports direction finding scenarios for multi-channel receiver testing. The hardware capabilities of the Rohde and Schwarz vector signal generators, together with the Rohde and Schwarz pulse sequencer software, give you a powerful tool to generate radar signals. So, you get a powerful radar signal simulator, which is made up of standard PC software, off-the-shelf signal generators, which are ultra-flexible because they can be expanded to multi-channel setups in case you have to test multi-channel receivers. Additional information for further reading can be found on our website. You can check out our options K300, K301 and K308 for signal generation. For extended sequencing, you can check out option 501. In order to get more information about scenario definition, you can read application cards on the pulse sequencer. If you are more interested in multi-channel signal generations or phase coherent, you can also read our signal application card on multi-channel coherent signal generation. Ladies and gentlemen, thank you very much for listening, and I hope there will be some questions afterwards.